Okay, so if we consider our theropod dinosaurs, we've got lots of big theropod dinosaurs that exist in many clades, and we have lots of small theropod dinosaurs that also exist in many clades. The Maniraptora is something we've talked a lot about, but I want to talk about some other features. Here I've just written lots of other stuff. There are a lot of features that arise in our more derived theropod dinosaurs. One of the things we were talking about recently was the arm proportions and how those change, and the feathers and how those change. Something else I want to look at is how the relative length of the shin bone and foot bones changes, as even if our dinosaurs are getting smaller overall, our theropods end up with shorter femurs relative to longer tibias. Now, we can look at that in this way. Here's our Sinosopteryx, all right, and it has fairly even length of these bones. But then if we look at our Caudopteryx, which is now one of our Maniraptorans, which the fancy wrists, this animal has a shorter femur and longer shin and foot. If we keep looking at more derived theropods and we look at our Archaeopteryx, short femur, long shin and foot, and these foot bones that are still distinct many different bones in our less derived theropods. If we look at our very derived theropods moving into Confuciusornis and finally into a pigeon, we end up with this sort of what I like to call the super foot bone between the ankle and the toes that is all sort of a big fused foot contraption. It's called the tarsometatarsus. So the shorter femur relative to the rest of the limb is a thing that we can track bit by bit through these animals. And again, I am not saying that a Sinosopteryx became a Caudopteryx, became an Archaeopteryx, became Confuciusornis, became a pigeon. That's not how this works. We know that these things are sharing last common ancestors. So when I show you differences between animals, don't think, oh, well, that animal turned into that animal and exaggerated that trait. Think there is a last common ancestor, and as we move up into a more refined clade, we can be thinking about those traits getting exacerbated. Here is that jump where the tail goes from being a long bony tail to a little stumpy pygostyle, all right? Now, one of my favorite animals to observe this today is our friend, the flamingo, because if we look at the flamingo, we look very closely at this smooth ankle, smooth hips. We've got ourselves a dinosaur, but the femur is one of the shortest bones on its body. Not just the femur, tibia, tarsometatarsus, super foot bone, and toes. Here is the ankle, all right? This femur fitting right into the hip socket, I want to pay a little bit more attention to hips right now. Check out this big, ridiculous pelvis, all right? This big, ridiculous pelvis is something that we've seen before when we consider the adult birds that live today. They have what I like to call a super pelvis. So if you get a rotisserie chicken and you pull it apart and you're kind of like, I don't really know what's going on here. I got the breast parts and I got the limbs, and then what is all of this stuff? It's a super pelvis. All right. And to really appreciate the super pelvis, it's helpful to look at a baby bird as well. So this is a juvenile bird, right? And we have the spine here and the different individual bones that make up the pelvis, right? But when this bird is an adult, the different bones that make up the pelvis have sort of fused together. That hip socket hole is right there. And they have fused together not only with the pelvis bones themselves, but the sacral vertebrae, those lower back vertebrae, those have also fused all together, and those bones have literally grown into each other. And we think if we look at the fully expressed traits in an adult animal, and we look at the juvenile intermediate traits that are not fully expressed in the juvenile animal, that can help us consider what we should look for in less derived dinosaurs. Now, in terms of what the hell is going on with this super pelvis, one of the reasons I want to bring it up is consider the flamingo. Flamingos do a really cool thing, which is they stand on one foot. You may have seen a flamingo standing on one foot and wondered, how do they do that? Well, it turns out that the balance given to this animal via the super pelvis the architecture of the leg bones, and then the balance with the whole rest of the animal allows these animals to sit with effectively all of their muscles at rest. So they can stand on their tippy toes. The ankle is here. All of this is foot, and these are the toe bones here. And when this animal is asleep, what these researchers did, Chang and Ting, what these researchers did was to, let a live flamingo sit on a little scale that would weigh exactly where its toes were pressing into the scale. And when it was asleep, here's a picture of the foot of the flamingo, right? This flamingo foot, here's a picture of the flamingo foot. When the animal was kind of asleep and hanging out, all of the pressure is directly under that tarsometatarsus, that super foot bone, which is directly down from the animal. So the super pelvis that's hidden in here, and all of these leg bones are allowing this animal to just stand stock still and put all of its pressure exactly here, with a big floppy foot probably helping so it doesn't fall into the mud, right? If the animal is still sitting still, but kind of alert and kind of glancing around and just kind of sitting, then it wiggles a little bit. And if the animal is still standing on one foot, but is moving around, is eating, is active, then actually the weight shifts a little bit more to the inner part of the foot, closer to the midline of the body. So all of this ridiculous balance leads to my favorite observation about flamingos, which is that if you try to get a dead flamingo to stand up on two legs, it won't work. But if you try to get a dead flamingo to stand up on one leg, you can do it. And these researchers did it. So when flamingos are standing on one leg, that is because the architecture of their super pelvis and their limb bones is allowing them to basically use zero energy to just stand there. This standing moves their body up away from the ground where there are bugs and bacteria and all kinds of stuff crawling around. It's not getting in their feathers. And they can be standing in water or mud or on sand or near a nest, and they can be moving their body up away from the substrate they're standing on without exerting any effort whatsoever.